Scientists discover surprising, hidden activity of semiconductor material. New research indicates that materials traditionally ignored in the design of computer chips are crucial for processing information. This breakthrough could pave the way for quicker and more efficient electronics, theoretical insights, and collaborative discoveries. To understand these findings, the theory and simulation effort, led by Long-Ching Chen, Hamer Professor of Materials Science and Engineering, Professor of Engineering Science and Mechanics and of Mathematics at Penn State, developed a theoretical framework to explain the entire process of the film and the substrate bulging instead of shrinking. When their model incorporated naturally occurring missing oxygen atoms in this material of two types, charged and uncharged, the experimental results could be satisfactorily explained. These neutral oxygen vacancies hold a charge of 2 electrons, which they can release when the material switches from an insulator to a metal, Gopalin said. The oxygen vacancy left behind is now charged and swells up, leading to the observed surprising swelling in the device. This can also happen in the substrate. All of these physical processes are beautifully captured in the phase field theory and modeling performed in this work for the first time by the postdoc Yin Shi in Professor Chen's group. Gopalin credited the multidisciplinary team's combined expertise in material growth, synthesis, structure analysis, and synchrotron beamline operation with the new understanding, using a collaborative approach led by Greg Stone, a physical scientist with the U.S. Army and the lead experimental author, and Yin Kai, postdoctoral scholar at Penn State and the lead theory author. The researchers disentangled the material's responses and observed them individually using phase field simulations, a simulation that helps scientists understand material changes over time by depicting various states of matter in a virtual setting. By bringing these experts together and pooling our understanding of the problem, we were able to go far beyond our individual scope of expertise and discover something new, said Roman Engel Herbert, director of the Paul Drude Institute of Solid-State Electronics in Berlin, Germany, and co-author of the study whose group grew these films along with Daryl Schlamm's group at Cornell University. Recognizing the potential of functional materials necessitates an appreciation of their broader context, just as complex scientific challenges can only be solved through widening our individual perspectives. The collaboration enabled both a significant amount of progress to happen in a short period of time and work to be done in a shorter period of time, and brought in a variety of perspectives from multiple disciplines. The responses themselves require further investigation, researchers said, but they believe that understanding them will assist in identifying previously unknown capabilities of vanadium dioxide, including potential yet to be discovered phenomena in the titanium-4 oxide substrate that was considered passive before this study. The study itself unfolded over 10 years, Gopalin noted, including validating the results. This is what it takes to go from interesting science to a working device you can hold in the palm of your hand, Gopalin said. Experiments and theory are complex and require large-scale collaborative teams working closely together over an extended period of time to solve difficult problems that could have a large impact. We hope and expect that this will accelerate the progress towards a new generation of electronic devices.